We shall now discuss on chapter 4 with some additional properties of nonlinear spaces and Banach spaces. Already we have been introduced with nonlinear spaces and Banach spaces with some results. Here we shall put some basic results and further results on nonlinear spaces and Banach spaces. Here we shall discuss on some geometric structure of some sets called convex sets on a linear space and a nonlinear space. Also we shall introduce some equivalent norms on a nonlinear space with some examples and some basic properties. Also we shall discuss on characterization of completeness of a nonlinear space with the introduction of series, that is infinite series on a nonlinear space. Also we shall discuss on factor spaces called quotient spaces on a nonlinear space, and thereby we shall show it will be a Banach space. We shall now discuss on module 1 of chapter 4. The title of module 1 is on convex sets. Let us take a definition. Let X be a linear space over a field capital F. The field F either may be reals or may be complex. Let x1 and x2 be any two elements of capital X. The set of all elements of the form y equal to alpha x1 plus 1 minus alpha into x2, where 0 less or equals to alpha less or equals to 1 is called the line segment joining the points x1 and x2. A set C subset of capital X is called convex if all segments joining any two points of the set capital C are contained in the set. Clearly, every subspace M of capital X is a convex set. In Euclidean space, the cube, circle, sphere, triangular area, in Euclidean 2 space, Euclidean plane and the line segments are all convex sets. Now, we take a note. Thus, a set capital C is convex in capital X if for all scalars alpha in 0 less or equals to alpha less or equals to 1, alpha C plus 1 minus alpha C is a subset of C. Equivalently, for any two reals alpha comma beta with 0 less or equals to alpha comma beta less than 1, alpha C plus beta C subset of C. Now, let us take a theorem. Intersection of any number of convex sets in a linear space is a convex set, but their union may not be so. The proof looks like this. Suppose collection of C alpha where alpha belongs to delta, delta being the indexing set, be a family of convex sets in a nonlinear space capital X, and let C equal to intersection C alpha, and intersection is taken over alpha belongs to delta where delta is an indexing set. Without loss of generality, let C is non-empty, that is C not equal to phi, and take any two members x and y of C. So, that is why we have taken x comma y belongs to capital C. Let 0 less or equals to beta less or equals to 1. Since x comma y belongs to C, so x comma y belongs to intersection of C alpha where alpha belongs to delta. So, x comma y belongs to C alpha for every alpha belonging to delta, and since each C alpha is convex, beta x plus 1 minus beta y belongs to C alpha. This is true for every alpha belongs to delta, and hence beta x plus 1 minus beta y belongs to intersection of C alpha where alpha belongs to delta, and intersection of C alpha where alpha belongs to delta is assumed equal to C. So, beta x plus 1 minus beta y belongs to C, and thus C is shown to be a convex set in capital X. Union of two convex sets may not be a convex set. Every triangular region in Euclidean plane is a convex set, but the figure looks like this: joining of the two triangle left hand side and right hand side as a union of two such convex sets fails to be a convex set. A subset C of a linear space capital X is convex if and only if alpha C plus beta C equal to alpha plus beta C for all positive scalars alpha and beta. Now, we go to the proof. For all scalars alpha and beta, we have alpha plus beta C subset of alpha C plus beta C. This is known as equation number 1. If capital C is convex and alpha and beta are positive scalars, we have alpha by alpha plus beta C plus beta by alpha plus beta c is a subset of C, because alpha by alpha plus beta by alpha plus beta is equal to 1. So, alpha plus beta c plus beta by alpha plus beta c subset of C implies alpha c plus beta c subset of alpha plus beta c. So, this is equation number 2. Combining the earlier results 1 and 2, we get alpha c plus beta c is equal to alpha plus beta c. Conversely, suppose alpha plus beta c equal to alpha c plus beta c holds for all positive scalars alpha and beta. Let us take a scalar gamma which lies between closed interval 0 and 1. Take alpha equal to gamma and beta equal to 1 minus gamma. Then we see that gamma c plus 1 minus gamma c equal to C. We know that every set is a subset of itself. So, C is a subset of C, and hence gamma c plus 1 minus gamma c subset of C. This implies that C is a convex set. Thus, we have proved the theorem. Let us take another theorem. If capital A and capital B are two convex sets in a linear space capital X, then A plus B is again a convex set in capital X. That is, sum of two convex sets is again a convex set. Now, the proof goes below. Now, A plus B equal to set of all such elements A plus B, where A is taken from capital A, B is taken from capital B. Let x comma y belongs to A plus B. So, x can be written as A1 plus B1 for some A1 belongs to capital A and for some B1 belongs to capital B. Similarly, as y belongs to capital A plus B, y can be written as y equal to A2 plus B2 for some A2 belongs to capital A and for some B2 belongs to capital B. Let us take a scalar lambda which lies between closed interval 0 and 1. Now, lambda x plus 1 minus lambda y is equal to lambda into A1 plus B1 plus 1 minus lambda into A2 plus B2. As we have taken x is equal to A1 plus B1 and y equal to A2 plus B2. Thus, lambda x plus 1 minus lambda y equal to lambda into A1 plus B1 plus 1 minus lambda into A2 plus B2, which on simplification we get lambda A1 plus 1 minus lambda A2 plus lambda B1 plus 1 minus lambda into B2. As A is convex and A1 A2 belongs to capital A, lambda A1 plus 1 minus lambda A2 belongs to capital A. As B1 belongs to B, B2 belongs to B and B is convex. So, lambda B1 plus 1 minus lambda into B2 belongs to B. So, lambda A1 plus 1 minus lambda A2 plus lambda B1 plus 1 minus lambda B2 belongs to A plus B, and hence it follows that A plus B is a convex set in capital X. If C is a convex set, then for any scalar alpha, alpha C is also a convex set. That means product of any convex set by a scalar is again a convex set in a linear space. We know that alpha C is equal to collection of all such elements alpha C, where C is taken from capital C. Let us take two elements x comma y belongs to alpha C. As x belongs to alpha C and alpha C is the collection of all such elements alpha C, where C belongs to capital C. So, x can be written as x equals to alpha C1 for some C1 belongs to capital C and y belongs to alpha C. So, y can be written as y equal to alpha C2 for some C2 belongs to capital C. Let us take a scalar lambda which lies between 0 and 1, that is the closed interval 0 and 1. Now, lambda x plus 1 minus lambda y is equal to lambda into alpha C1 plus 1 minus lambda into alpha C2, which is equals to alpha into lambda C1 plus alpha into 1 minus lambda into C2, which is equal to alpha into lambda C1 plus 1 minus lambda into C2. This belongs to C, as C is convex, because lambda C1 plus 1 minus lambda into C2 belongs to capital C. So, alpha C is a convex set in X. Let us take a theorem, that is a sphere in a nonlinear space is a convex set. Now, the proof goes below. We prove the theorem for a closed sphere. we prove the theorem for a closed sphere. The proof is analog for the open sphere also. Let x1, x2 belongs to SR third bracket A. SR third bracket A is the closed sphere centered at A with radius r. As x1 belongs to SR third bracket of A, we get norm of x1 minus A less or equals to r. As x2 belongs to SR third bracket A, norm of x2 minus A less or equals to r. Let us take y equal to tx1 plus 1 minus t into x2, where t belongs to the closed interval 0, 1. Then norm of y minus a equal to norm of tx1 plus 1 minus t x2 minus a, because y equal to tx1 plus 1 minus t x2 is assumed. Now a can be written as ta plus 1 minus ta into a. So norm of tx1 plus 1 minus t x2 minus a is equal to norm of tx1 plus 1 minus t into x2 minus ta minus 1 minus ta into a, which is less or equals to norm of tx1 minus ta plus norm of 1 minus t into x2 minus 1 minus t into a by the triangle inequality property of the norm axiom 3, which is again equals to t into norm of x1 minus a plus 1 minus t into norm of x2 minus a. As norm of x1 minus a less or equals to r and norm of x2 minus a less or equals to r, so we get t into norm of x1 minus a plus 1 minus t into norm of x2 minus a less or equals to tr plus 1 minus t into r, which is equal to r. So y belongs to SR third bracket A, and hence SR third bracket A is a convex set. Let capital X be a nonlinear space over a field capital F and K be a convex subset of capital X. Then the closure of K, that is K bar, is also a convex set. Now we go to the proof. If x comma y belongs to K bar, that is the closure of K, and let epsilon greater than 0 be arbitrary. So there exists x1 comma y1 belonging to K such that norm of x minus x1 is strictly less than epsilon and norm of y minus y1 is strictly less than epsilon. Let us take an element t belongs to the closed interval 0, 1. Then norm of tx plus 1 minus t into y minus tx1 plus 1 minus t into y1 is less or equals to t into norm of x minus x1 plus 1 minus t into norm of y minus y1 by norm axiom property N3, which is again less than t epsilon plus 1 minus t into epsilon. This equal to epsilon. Since K is convex, t into x1 plus 1 minus t into y1 belongs to capital K, and because epsilon greater than 0 is arbitrary, t x1 plus 1 minus t into y belongs to K bar, showing that K bar is a convex set in a nonlinear space capital X. Let us take another theorem. Let X be a linear space and K is a subset of X, which is a convex set. If x1 comma x2 comma dot 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 xn belonging to capital K, then all elements of the form alpha 1 x1 plus alpha 2 x2 plus dot dot alpha n xn, where alpha I greater or equals to 0 with alpha 1 plus alpha 2 plus dot dot alpha n is equal to 1, and alpha 1 x1 plus alpha 2 x2 plus alpha n xn belonging to capital K. We now prove the theorem by induction. If n is equal to 2, the theorem is true because capital K is convex. We therefore assume that the theorem is true for n minus 1, and we shall prove it for n. We may assume that alpha 1 plus alpha 2 plus dot 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 plus alpha n minus 1 is greater than 0, because if alpha 1 plus alpha 2 plus dot 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 plus alpha n minus 1 is equal to 0, then each alpha 1 alpha 2 dot dot alpha n equal to 0. And so alpha 1 x1 plus alpha 2 x2 plus dot dot alpha n minus 1 xn minus 1 plus alpha n xn is equal to alpha n xn, which is again equal to xn. As xn belonging to K, so alpha 1 x1 plus alpha 2 x2 plus alpha n minus 1 xn minus 1 plus alpha n xn belongs to K. As alpha n equal to 1 and sigma I equal to 1 to n alpha I equal to 1, and this proves the theorem. Up to this we have learned what is a convex set in a linear space. Also we have learned that a open sphere, a closed sphere is again a convex set. Also we have discussed that intersection of any number of convexes is again a convex set. We shall now additional property on convex hull, which is the intersection of all convex sets containing a given set. We shall now discuss on convex hull of a set. Let us take a definition of a convex hull of a set. Let capital S be a non-empty subset of a linear space capital X. Then the convex hull of capital S denoted by conv hull of S is the intersection of all convex sets in capital X containing S. So, convex hull of S is the smallest convex set in capital X containing S. We know that arbitrary intersection of all convex sets is again a convex set, and since convex hull of S is the smallest convex set in X containing S. Now, let us take a theorem called the representation theorem for convex hull. Convex hull of S consists of all vectors x is equal to alpha 1 x1 plus alpha 2 x2 plus dot 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 plus alpha n xn, that is x is equal to sigma I equal to 1 to n alpha I xi, where x1 comma x2 comma dot dot xn belonging to capital S and alpha I get out equals to 0 with sigma I equal to 1 to n alpha I is equal to 1 and index n is not fixed. The proof follows by principle of mathematical induction. Let capital T be the collection of all vectors x is equal to sigma I equal to 1 to n alpha I xi, where x1 comma x2 comma dot dot xn belonging to capital S with sigma I equal to 1 to n alpha I equal to 1, and index n is not fixed. For n is equal to 1, every element of capital S is an element of capital T, that is S is a subset of capital T. We shall now prove that capital T is convex. Let u comma v belongs to capital T, where u is equal to sigma I equal to 1 to n alpha I xi, where x1 comma x2 comma dot dot xn belonging to capital S and alpha I get out equals to 0 with sigma I equal to 1 to n alpha I equal to 1, and v equals to sigma I equal to 1 to m beta I xi, where x1 comma x2 comma dot dot xm belonging to capital S and beta I get out equals to 0 and sigma I equal to 1 to m beta I equal to 1. Here n and m may be different or may be equal. Let 0 less or equals to gamma less or equals to 1. So, gamma u plus 1 minus gamma into v is equal to gamma into sigma I equal to 1 to n alpha xi plus 1 minus gamma into sigma I equal to 1 to n beta I xi, because u is equal to sigma I equal to 1 to n alpha I xi and v is equal to sigma I equal to 1 to m beta I xi, which on simplification we get sigma I equal to 1 to n gamma alpha I xi plus sigma I equal to 1 to m 1 minus gamma into beta I xi. Now, gamma alpha I get out equals to 0 and 1 minus gamma into beta I get out equals to 0 for I equal to 1 to m and for I equal to 1 to up to n. But sigma I equal to 1 to n gamma alpha I plus sigma I equal to 1 to m 1 minus gamma into beta I is equal to gamma into sigma I equal to 1 to n alpha I plus 1 minus gamma into sigma I equal to 1 to m beta I, which is again equals to gamma plus 1 minus gamma, and that is equal to 1. So, gamma u plus 1 minus gamma into v belongs to capital T, and it shows that capital T is convex and S is a subset of T, and consequently convex hull of S is a subset of T. This is equation number 3. We shall now prove for the reverse inclusion relation, that is T is a subset of convex hull of capital S. Let capital W be any convex set containing capital S. For n is equal to 1, every element of capital T is an element of capital S, and consequently every element of T is an element of W. Let us consider that the result is true for n equal to m, that is it is true for m number of elements. That is, if x is equal to sigma I equal to 1 to m alpha I xi, where x1 comma x2 comma dot dot xm belonging to capital S and alpha I get out equals to 0, where I equal to 1 to up to m with sigma I equal to 1 to m alpha I is equal to 1. then X is an element of capital W. Let n is equal to m plus 1 and X is equal to sigma I equal to 1 to m plus 1 alpha I xi, which belongs to capital T, where alpha I greater or equals to 0 and I equal to 1 to up to m plus 1 with sigma I equal to 1 to m plus 1 alpha I is equal to 1. Let us take beta equal to alpha 1 plus alpha 2 plus dot 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 plus alpha m, then beta is greater than 0. Put beta I is equal to alpha I by beta, and this is meaningful because beta is strictly greater than 0 and I equal to 1 to up to m. Then sigma I equal to 1 to m beta I equal to 1. Now x equal to alpha 1 x1 plus alpha 2 x2 plus dot 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 alpha m xm plus alpha m plus 1 xm plus 1 is equal to beta into beta 1 x1 plus beta into beta 2 x2 plus dot 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 plus beta into beta m xm plus 1 minus beta into xm plus 1, which is again equals to beta into within the first bracket beta 1 x1 plus beta 2 x2 plus dot 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 plus beta m xm plus 1 minus beta into xm plus 1. This belongs to capital T and T is a subset of W, as beta 1 x1 plus beta 2 x2 plus dot dot beta m xm belongs to capital W and xm plus 1 belongs to capital W and W is convex. So, x is equal to sigma I equal to 1 to m plus 1 alpha I xi belongs to capital W. Thus, the result is true by the principle of mathematical induction, that is every element of capital T is an element of capital W with S is a subset of W. As W is arbitrary, it follows that T is a subset of intersection of all W, where S is a subset of W, that is T is a subset of convex hull of S, and this is named as equation number 4. Combining 3 and 4, we get T equal to convex hull of S, and the theorem is proved. In this module, we have learnt on some properties of convex sets, also convex hull of a set, and we have also learnt the representation theorem for a convex hull. With this, we now come to an end of this module.